Good morning everyone. I hope you are all doing well. My name is Thaneshwar Kumar Sahu and I am excited to welcome you to today's lecture titled Digital Communication Systems Advantages and Limitations and Application for the course Fundamental of Communication Systems and its Applications. It's exciting to see so many of you joining us from different corners of the world. First and foremost, I want to extend a warm thanks for taking the time to be a part of this session. So, without further delay, let us move on to the topic titled Digital Communication Systems, Advantages and Limitations and its Applications. First, we will discuss about Introduction to Digital Communication System. Definition: digital communication systems convert data into digital signals, usually binary, and transmit this data across various channels. Unlike analog systems which use continuous signals, digital communication relies on discrete signals, typically representing two states 0 and 1. Overview of the system: the shift from analog to digital communication has revolutionized how information is transmitted, processed and stored. Digital communication allows for more precise, efficient and flexible methods for data transfer, essential in today's interconnected world. Now, we will discuss component of digital communication systems. Source: the origin of the data to be communicated, which could be anything from a text message to a video signal. The source generates the data that needs to be transmitted. Encoder converts the source data into a digital format. Encoding involves converting the analog signal into a digital one, usually through a process called quantization, which converts a continuous range of values into a finite range of discrete values. Channel: the medium through which the digital signal travels. This can be a physical medium like cables or a wireless medium like radio waves. The channel's characteristics affect the quality of the transmission, such as its bandwidth and susceptibility to noise. Next one is decoder. Reverses the encoding process, converting the digital signal back into its original form. The decoder ensures that the received data accurately reflects the transmitted data, accounting for any errors that may have occurred during transmission. Receiver: the endpoint of the communication system where the decoded data is received. The receiver must accurately interpret the data, which may involve further processing to remove any errors or noise introduced during transmission. Now, we will discuss about digital versus analog communication. Communication is fundamental to human interaction, and with the advancement of technology, the methods by which information is transmitted have evolved significantly. Communication systems can be broadly categorized into two parts: analog and digital. Both systems have their unique characteristics, advantages and limitations. Understanding the differences between them is crucial for appreciating the modern shift toward digital communication. Analog communication. Analog communication involves the transmission of data through continuous signals that vary in amplitude, frequency or phase. These signals represent information in a form that closely resembles the original data. For example, in analog audio transmission, the variations in sound waves are directly translated into corresponding variations in voltage or current, which are then transmitted over a medium like copper wire or air waves. One of the most prominent example of analog communication is the traditional AM or FM radio. In this system, sound is converted into an electrical signal, modulated to a specific frequency and transmitted. The receiver then demodulates the signal and converts it back into sound. Analog communication is also used in television broadcasting, telephony and other forms of media transmission. Digital communication. Digital communication, on the other hand, involves the transmission of data through discrete signals, typically in binary forms, zeros and ones. Instead of varying continuously, the signal jumps between distinct levels, representing different pieces of information. Digital communication requires the data to be converted into a digital format through processes such as sampling, quantization and encoding before transmission. A typical example of digital communication is the transmission of data cover the internet, where transmission such as text, images and video is broken down into packets of binary data and transmitted across various networks. Mobile communication networks, that is 4G and 5G, digital television and voice over internet protocol are other examples where digital communication is extensively used. Now, we will discuss about comparison of analog and digital communication systems. First is signal representation. Analog communication uses continuous signals that vary smoothly over time. These signals directly correlate with the information being transmitted, whether it is sound, light or another form of data. Digital communication uses discrete signals representing information as a series of zeros and ones. The original data is sampled at specific intervals and each sample is converted into a binary number. Second is noise and interference. One of the major drawbacks of analog communication is its susceptibility to noise and interference. Since analog signals are continuous, any disturbance in the transmission medium can alter the signal, leading to degradation in quality. For example, static noise in radio broadcast or signal distortion in analog television. In digital communication is more robust against noise because the receiver only needs to distinguish between discrete levels, that is high and low voltage for binary signals. Even if noise slightly alters the signal, as long as the changes do not push the signal beyond the threshold, the receiver can correctly interpret the data. Third is bandwidth usage. Analog communication typically requires less bandwidth than digital communication for transmitting a similar amount of data. However, the actual bandwidth requirements depend on factors such as the modulation technique and the desired quality of transmission. Digital communication often requires more bandwidth, particularly because of the need to sample the signal at a high rate according to the Nyquist theorem and transmit additional bits for error detection and correction. However, digital compression techniques can mitigate this by reducing the amount of data that needs to be transmitted. Fourth is error detection and correction. In analog communication, error detection and correction are challenging because any noise or interference directly alters the signal. Once an analog signal is distorted, it is difficult to recover the original data, but digital communication systems can incorporate sophisticated error detection and correction algorithms. Techniques such as parity checks, checksums and more advanced error correcting codes like Hamming codes or Reed-Solomon codes ensure that errors introduced during transmission can be detected and in many cases corrected. Fifth is data security. Analog signals can be intercepted and interpreted relatively easily, making them less secure for transmitting sensitive information. In digital communication allows for the encryption of data, making it much more secure. Encrypted digital data can be transmitted over networks with a lower risk of interception and unauthorized cases. Sixth is complexity and cost. Analog communication systems are generally simpler and cheaper to implement, especially for short distance and low frequency applications. For instance, analog radios are relatively simple devices with fewer components compared to digital ones. In digital communication systems are more complex, requiring sophisticated encoding, modulation and processing equipment. This complexity can increase the cost to advance in technology have significantly reduced the price of digital communication devices over time. Now, we will discuss about advanced feature of digital communication. First, error detection and correction. One of the most critical feature of digital communication is the ability to detect and correct errors that occur during data transmission. In digital communication, data is transmitted in binary form, zeros and 1, and any description in the transmission medium can cause errors. Advanced digital communication systems employ various error detection and correction techniques to ensure data integrity. Error detection methods such as parity checks, cyclic redundancy checks, and checksums are used to detect errors in the transmitted data. These techniques add extra bits to the data stream, allowing the receiver to identify discrepancies between the received data and the expected data. Error correction, more sophisticated methods such as Hamming codes, Reed-Solomon codes and convolutional codes not only detect errors but also correct them. This is particularly useful in applications where data integrity is crucial, such as in satellite communication, deep space missions and data storage systems. Second is data compression. Data compression is an essential feature of digital communication that reduces the amount of data that needs to be transmitted or stored without significantly compromising quality. This is particularly important for application involving large amount of data such as video streaming, audio transmission and file storage. Lossless compression. Techniques such as Huffman coding, Lempel-Zhu-Welch compression and run length encoding compress data without any loss of information. The original data can be perfectly reconstructed from the compressed data. Lossless compression is used in applications where data integrity is critical, such as text files, medical imaging and legal documents. Lossy compression. Techniques like JPG for images and MP3 for audio reduce the size of the data by removing some of the less critical information. While this results in a loss of quality, it significantly reduces the amount of data, making it ideal for multimedia applications where perfect fidelity is less important than reducing bandwidth or storage requirements. Third is encryption and security. With the increasing importance of data privacy and security, digital communication systems have incorporated advanced encryption techniques to protect data from unauthorized access. Encryption converts data into a form that can only be understood by those with the appropriate decryption key. Techniques such as advanced encryption standard, RSA encryption and elliptic curve cryptography are widely used to secure data in transit and at rest. Encryption is vital for applications such as online banking, secure email and confidential communications. Authentication and access control. Digital communication systems often include mechanisms for ensuring that only authorized users can access certain data. Techniques such as digital signatures, two-factor authentication and biometric verification are used to authenticate users and control access to sensitive information. Fourth is multiplexing and multiple access. Multiplexing is the process of combining multiple signals into one signal for transmission over a shared medium, which optimizes the use of available bandwidth. Time division multiplexing. Time division multiplexing allocates time slots to each signal, allowing multiple signals to share the same transmission medium. This is commonly used in telecommunication systems where multiple phone calls are transmitted over the same wire. Frequency division multiplexing FDM. FDM assigns different frequency bands to each signal, enabling simultaneous transmission of multiple signals. This is used in radio broadcasting where different stations transmit at different frequencies. Code division multiple access CDMA. CDMA allows multiple users to share the same frequency band by assigning unique codes to each user's signal. This is widely used in mobile communication networks such as 3G. Fifth is modulation techniques. Advanced modulation techniques are essential for optimizing the transmission of digital signals over various communication channels. These techniques enhance the efficiency, reliability and quality of digital communication. Next is phase shift keying PSK. PSK modulates the phase of a carrier signal to represent binary data. Variants such as binary PSK, BPSK and quadrature PSK, QPSK are used to increase the data rate and reduce error rates. Quadrature amplitude modulation QAM. Quadrature amplitude modulation combines amplitude and phase modulation to increase the amount of data that can be transmitted in a given bandwidth. This technique is widely used in digital television, cable modems and broadband communications. Sixth is digital signal processing DSP. Digital signal processing is a key feature in modern digital communication systems, enabling the analysis, manipulation and improvement of digital signals. Filtering. DSP techniques allow for the filtering of noise and unwanted signals, improving the clarity and quality of the transmitted data. Signal compression. DSP is used in compressing signals for more efficient transmission and storage, particularly in audio and video applications. Adaptive filtering. Adaptive filtering techniques adjust filter parameters in real time to optimize performance based on the changing characteristics of the signal and the transmission environment. Now, we will discuss about limitations of digital communication systems. First, bandwidth requirement. Digital communication systems often require significantly more bandwidth than analog systems. This is primarily due to the need for high sampling rates and the transmission of additional bits for error detection and correction. For instance, transmitting high definition video or large volumes of data can strain network resources, leading to congestion and requiring expensive infrastructure to support high data rates. In scenarios where bandwidth is limited, such as in remote areas or with older network technologies, digital systems may face challenges in providing the desired quality of service. Second is complexity and cost. The complexity of digital communication systems is another limitation. These systems require sophisticated hardware and software for encoding, modulation, error correction and data compression. The implementation of such systems often involves complex algorithms and high computational power, leading to increased cost in both development and deployment. Additionally, the need for regular updates and maintenance to keep up with technological advancements further adds to the cost, making digital system less accessible in low resource environments. Third is latency issues. Latencies or the delay between the transmission and reception of data can be more pronounced in digital communication systems. This is especially true when complex encryption, error correction and compression algorithms are used. For applications requiring real-time communication such as online gaming, video conferencing and remote surgery, even a small delay can significantly impact performance and user experience. High latency can lead to lag, delays and disruption in communication, which can be critical in time-sensitive applications. Fourth is power consumption. Digital communication systems, particularly those used in wireless networks and mobile services, tends to consume more power than their analog counterparts. The need for continuous data processing, encryption and error correction increases the energy demand, leading to shorter battery life in mobile devices and higher operational cost in large scale networks. This can be a significant drawback in environments where power efficiency is critical, such as in portable devices or remote sensing applications. Fifth is susceptibility to jamming and interference. While digital communication systems are generally more resistant to noise than analog systems, they can be more susceptible to jamming and interference. Digital signals require precise timing and synchronization. Any disruption in the signal can cause data loss or corruption. In hostile environments such as military operations or areas with high electromagnetic interference, digital communication systems may struggle to maintain reliable connections. Now, we will discuss about digital communication system applications. Digital communication systems have become an integral part of modern life, facilitating the seamless exchange of information across various platforms and industries. Their applications are vast and diverse, impacting everything from personal communication to global business operations. First, telecommunications. One of the most prominent applications of digital communication systems is in telecommunications. Mobile networks, including 4G and 5G, rely on digital signals to transmit voice, text and multimedia data. Digital communication enables high-speed internet access, clear voice calls and real-time video streaming, revolutionizing how we connect with others worldwide. Second is broadcasting. Digital communication is essential in broadcasting, particularly in television and radio. Digital TV and radio provide better quality audio and video than analog systems, along with additional features such as multiple channels, interactive services and electronic program guides. The switch from analog to digital broadcasting has also allowed more efficient use of the available spectrum, enabling the transmission of more channels and services. Third is internet and data communication. The backbone of the internet is built on digital communication systems. Data communication, including email, web browsing, file transfers and cloud computing, relies on digital communication like TCP or IP to transmit information efficiently and securely across the globe. Digital communication has also enabled the rise of VoIP, Voice over Internet Protocol services, allowing voice communication over the internet. Fourth is satellite communication. Satellite communication in digital communication systems are crucial in satellite communication used for global positioning system GPS, weather monitoring and television broadcasting. Satellites transmit digital signal across vast distances, providing critical data for navigation, environmental monitoring and global communications. Fifth is healthcare. In healthcare, digital communication is used in telemedicine, where patients can consult with healthcare professionals remotely through video calls. Medical imaging, electronic health records and digital diagnostics also rely on digital communication to store, transmit and analyze patient data, improving the quality of care. Sixth is industrial automation. Digital communication systems play a vital role in industrial automation, where machines and sensors communicate with each other to streamline manufacturing processes, increase efficiency and reduce human interventions. This technology is at the heart of the Industrial Internet of Things IIoT, where interconnected devices work together to optimize production and maintenance. Now we will discuss about telecommunication and networking. Mobile networks. Digital communication is at the heart of mobile networking, enabling technologies like 4G and 5G. These networks provide high speed data connectivity, enabling services like video streaming, online gaming and real time communication. VoIP, Voice over Internet Protocol, uses digital communication to transmit voice data over the internet. VoIP has become a popular alternative to traditional phone services, offering cost saving, flexibility and integration with other digital services. Satellite communication. Satellite rely on digital communication to transmit data across vast distances, providing global coverage for services like GPS, satellite TV and internet access in remote areas. Now we will discuss about digital broadcasting. Digital TV, digital television offers better picture and sound quality, more channels and additional features like interactive TV, electronic program guides and on-demand services. Digital TV also uses less bandwidth than analog TV, allowing for more efficient use of the broadcast spectrum. Now we will discuss about radio broadcasting. Digital radio provides clearly sound quality and more channels than analog radio. Digital radio also offers additional features like text information, program guides and the ability to pause and rewind like a live broadcast. Streaming services. Digital communication enables streaming services like Netflix, Spotify and YouTube, allowing users to access a vast library of content on demand. These services have transformed the media industry, offering convenience, personalization and new business models. Now we will discuss about data transmission and storage. Cloud computing. Cloud computing relies on digital communication to store, process and transit data over the internet. Cloud services like Google Drive, Dropbox and AWS allow users to access their data from anywhere, providing flexibility, scalability and cost saving. File sharing. Digital communication enables file sharing technologies like FTP, P2P networks and cloud-based file sharing services. These technologies allow users to share large files quickly and easily, supporting collaboration, content distribution and data backup. Data centers. Data centers are the backbone of digital communication systems, hosting vast amount of data and providing the infrastructure for online services. Data centers use advanced digital communication technologies to ensure data is transmitted securely, efficiently and reliably. Now we will discuss about the healthcare applications of digital communication systems. Telemedicine. Telemedicine uses digital communication to provide remote healthcare services, allowing patients to consult with doctors, receive diagnosis and access treatment without visiting a healthcare facility. Telemedicine has become increasingly important in rural and underserved areas where access to healthcare is limited. Remote monitoring. Digital communication enables remote monitoring of patients' vital signs, allowing healthcare providers to track their conditions in real time. This is particularly useful for managing chronic conditions, post-operative care and elderly patients. Electronic health records. Electronic health record use digital communication to store and transmit patients' medical records securely. Now we will conclude. Digital communication systems offer numerous advantages including noise immunity, data security and error detection. However, they also come with limitations like higher bandwidth requirements and complexity. Despite these challenges, digital communication has become essential in modern telecommunications, broadcasting, data storage, healthcare and more. In final, the future use of digital communication is bright with ongoing advancements in technologies like 5G, quantum communication and artificial intelligence. As digital communication continues to evolve, it will play a crucial role in shaping the future of communication, connectivity and innovation. Thank you everyone for listening to the lecture.